Welcome to The Explainer. You know, every complex piece of tech you own has to solve this invisible but totally high stakes challenge. It's all about managing time. Specifically, what happens when different parts of a single computer chip are basically living in different time zones.
All right, so here's how we're going to break this down. First, we'll look at a chip's many clocks. Then, we'll dive into the danger of something called metastability. We'll check out a simple border check, see what happens when multiple signals try to cross at once, and finally, get into the really smart ways engineers get around all this.
Okay, first things first. You have to understand that a modern chip, it's not just one single thing. Think of it more like a bustling city, right? You've got all these different districts, and each one is running at its own pace, on its own schedule, with its own internal clock.
So that begs a really important question, right? Why make it so complicated? I mean, why not just have one single master clock for the whole chip? Wouldn't that be way easier and just avoid all these problems from the get-go? Well, it really boils down to two things: efficiency and power. You see, a modern chip is packed with all these specialized parts. You've got your super-fast processor core, a slightly slower memory controller, a USB controller, an audio codec. They all have different jobs and run at very different speeds. It makes zero sense to have a blazing fast processor just sit there twiddling its thumbs, waiting for a much slower USB port. So by giving each part its own optimized clock, its own unique heartbeat, the whole system just runs way, way more efficiently. And these separate time zones, that's what engineers call clock domains. And that brings us to this analogy, which is just perfect. Thinking of each clock domain as a country with its own time zone is the key. The real challenge, what engineers call clock domain crossing, or CDC. It isn't about the countries themselves. The problem is what happens when you try to send a messenger, your data, across that international border. So, what does happen when that messenger, our little packet of data, shows up at the border at the exact wrong time? Well, this is where things get really messy really fast.
Yeah, and as the experts Daly and Polton put it, timing is literally everything. In a digital circuit, decisions have to be made in an unbelievably tiny fraction of a second. We're talking about the most basic decision. Is this signal a 1 or is it a 0? But what if a signal from that other country arrives and changes right at the exact moment the receiving clock is trying to check it? Well, the circuit just can't decide. It gets stuck. And that failure, that stuck state, it has a name. It's called metastability. It's basically an unstable maybe state. It's not a clean 0 and it's not a clean 1. It's this weird, unpredictable, in-between voltage. And that moment of indecision, right down at the hardware level, is absolute poison for a digital system because the whole thing is built on clear, definite yes or no answers. And you can see the contrast right here. I mean, it's night and day. A normal digital signal is clear, predictable. The system can trust it. A metastable signal, it's just a mess. It's undefined, unpredictable, totally untrustworthy. The system has no idea what to do with it. Worse, different parts of the chip might look at that same messy signal and come to completely different conclusions. It's just total chaos. And this is where it gets really dangerous. That one little moment of indecision doesn't just stay in one place. Nope. It can spread through the new clock domain like a virus, corrupting data everywhere it goes. It leads to those weird glitches you sometimes see, or even worse, a full-on system crash, all from one tiny timing error. The consequences are huge. Okay, so if this is so incredibly dangerous, how on earth do engineers deal with it? How do you build a secure border checkpoint to manage these signals and stop metastability in its tracks? Well, the most common solution is actually brilliantly simple. It's called a 2 flip-flop synchronizer. Here's how it works. First, the signal arrives and gets captured by the first flip-flop. Now, this is the danger zone. This is where that metastability might happen. But, and this is the genius part, the system just waits. It gives it one full clock cycle for that wobbly, uncertain signal to settle down into a definite 0 or 1. Only after that waiting period does the second flip-flop come in and take a clean, stable reading. Problem solved. Now you might be wondering, is this thing foolproof? Well, not technically 100% of the time, no. It just makes failure really, really unlikely. And engineers have a way to measure this. It's a metric called mean time before failure, or MTBF. It's basically a statistical calculation that predicts, on average, how long a system can run before one of those nasty metastable events actually manages to sneak past that second checkpoint. And get this, For most serious chip designs, the goal isn't just to make failures rare. The goal is to design the circuit so that the calculated MTBF is longer than the age of the universe. Yeah, you heard that right. It's about making the chance of failure so ridiculously, astronomically small that, for all intents and purposes, it will never ever happen. Okay, so that 2 flip-flop synchronizer is great for a single bit, one messenger. But what if you need to send a whole group of signals at once? Not just one messenger, but a whole convoy, carrying a complex, multi-part message, like a number. Yeah, this is where things get tricky again. The problem is something called data skew. See, when you send multiple bits at once, they're all traveling on separate physical wires on the chip. And even if those wires are designed to be identical, tiny, tiny differences in length or temperature or voltage, they cause minuscule delays. So even though all the bits left at the exact same instant, they're not going to arrive at the border at the exact same instant. This is a perfect way to see the problem. Look at a simple binary counter going from 7 to 8. In binary, that's 0, 1, 1, 1, changing to 1, 0, 0, 0. Now look closely. To make that one single step, from 7 to 8, 4 different bits have to flip at the exact same time. All 4 have to change in the same nanosecond. So, knowing what we now know about data skew, what do you think happens if the receiving end tries to read that value right in the middle of that change, when some bits have flipped but others haven't yet? What kind of crazy garbage value might the system see? The scary answer is pretty much anything. You could get a 0, you could get 15, you could get 10. Any combination is possible because you're catching the value mid-transition. And this isn't just a minor glitch. This is the kind of error that makes a program jump to a totally wrong memory address or completely corrupts the data it's working on. It's a disaster. So how do engineers get that whole convoy across the border safely? Well, as you might guess, they've come up with some incredibly smart solutions. One of the most elegant solutions is to just change the language. Instead of standard binary, engineers use something called gray code. Now, gray code has this one magic property. When you count from one number to the next, only one single bit ever changes. That's it. So look here, going from 7 to 8, instead of 4 bits flipping like in binary, in gray code, just 1 bit flips. It's brilliant. And that one simple trick solves the entire problem. By converting the number to gray code before sending it, the whole issue of data skew just disappears. Because if only 1 bit is changing, there's no way to sample some scrambled in-between value. The worst thing that can happen is you might be a little late and read the old value, or you might read the new value, but you'll never read a completely wrong invalid number. It's so clever. Okay, another really common and powerful solution is to avoid a direct border crossing altogether. Instead, you build a sort of neutral, demilitarized zone in between. It's a shared memory buffer called an asynchronous FIFO, which stands for first in, first out. Think of it like a mailbox. The sending domain drops off data in the mailbox using its clock. Then, whenever it's ready, the receiving domain comes along and picks up the data using its clock. They never have to talk to each other directly, which completely and safely isolates the 2 time zones. So what's the big takeaway here? Well, the fact that your phone, your computer, pretty much the entire internet works as smoothly as it does, it all depends on these invisible, super elegant solutions to what is, at its heart, a fundamental problem of time. The next time you use any device, just think about the silent, incredibly complex ballet of signals happening inside, all managed by these clever tricks, just to make sure everything works perfectly. It really is amazing.